posted. Okay, I posted 2 lectures about threads and multi-threading. I hope you all watched them. If not, that's okay. Just means that you need to watch them as soon as possible. They are required for your homeworks, and I don't know. I think that I gave a very solid explanation of multi-threading. I've seen a lot of different explanations over time, so I kind of made an amalgamation of all of my favorite analogies and explanations and examples, split up into about an hour and a half of lecture material. So yeah, please watch. For helping me out on this. So this is multi-threading assignment. It's overall pretty simple. There's only a couple functions that you will need to implement for this. So, okay, by show of hands, who has seen this assignment? Anyone read through it yet? Okay, cool. So most of us at least have some idea of what's going on. I'll quickly kind of just skim through it. Yeah, is there a question? Should be all the way the bottom of the page in the multi-threading section. Yeah, homework 7. It's good. I need to refresh. Okay, other people have found it. So, okay, so the goal of this assignment, is to implement 2 different algorithms. One of them is sorting. The other one is fill prime Q. And so your goal is to take these, you're given 2 different single-threaded implementations, which I can pull up right here. So here is, this is the file that you are provided with the different algorithms. So here is the sort function. And you can see that you are given this single-threaded implementation right here, where this bubble sort helper function is called, and it's called and it sorts the function. And your goal is to now sort different chunks of an array, and then all in parallel. So you sort each tiny little chunk, and then at the end, then you combine them all together. So by sorting the different individual chunks, this will actually improve your time complexity, because now instead of it just being n squared for the entire thing, now it will be n divided by the number of chunks squared. So if you have potentially 8 threads, then now in theory, your sorting will be about 64 times faster, because now it's, the chunk sizes are the decreasing the size of the chunks parabolically increases the speed of the implementation. Okay, cool. This will make more sense if you watch the lectures that I already posted. The idea of how you can segment up an array and then work on different segments of an array is something that I already talked about. And then this second implementation, this requires you to implement the individual thread function, as well as a main caller function. So the point of this is you are just given an array of a bunch of random integers, and you just need to check for every single integer if it is prime. And if it is prime, then you go and push it onto this queue. So what you'll need to be careful of is if you ever push anything or if you're editing any sort of memory, then you need to make sure that you do not have a race condition. You want to make sure that if you ever write something to a bit of memory, that it is maintained if something else is trying to write to that same bit of memory at the same time. If there's contention, then you need to solve that contention with a mutex lock. Okay, good. Hope this will make sense once you read through it. Any questions on this? If anyone's had a chance to look at this? Yeah. Cool. I expect there to be more questions. It is due next Friday, as well as I will be posting the final homework assignment either today or tomorrow. And that will also be due next Friday. So in total, we will have 8 homeworks for this class, and they will all, the final one, will be due next Friday. Question? Yeah, so the goal is to turn these single-threaded implementations into a multi-threaded implementation to where now it's supposed to run faster. Exactly, yeah. So you're given unoptimized code. It's your goal to implement it in a more optimized way using multiple threads. Yeah, exactly. Yeah, thank you. Cool. Okay. So yeah, let me see. Let's have a conversation about threads really quick. I'll pull up the that's not it. Where is it? 1, 2, 6. Yeah. Okay. Can anyone define a thread, or at least tell me what goes inside of a thread? Yeah. 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 Yeah, exactly, right. So all the thread is you can just think of it as a program counter, and then also whatever data is associated with that. So maybe you have stack data, associated with that. So that's all a thread is. And what we're used to is usually just a single program has a single program counter. But what you can do is you can have a program create multiple threads, and now you will have multiple program counters that are all operating at like different parts of your code, all in parallel. So if you have a bit of code that maybe you are taking an array and you are like adding 1 to every single value in this array, then you can imagine you could add 1 to the first half of the array in one thread, and then in a completely different thread with a different program counter, then you add 1 to the second half of the array. And in theory now, this will make your program go twice as fast. Okay. By show of hands, how many of you have already heard of this topic before? Right? Okay, cool. Yeah, so we've all kind of seen this before. Has anyone actually done multi-threading before on any sort of project? Oh, okay, that's way higher than I was expecting. What classes or class did you learn multi-threading in? You can just shout it out. 130. Okay, fantastic. Yeah, great. Okay, that's the operating systems class? Oh, fantastic. Okay. So if we have this array, right, and we just add 1 to every single value in this array, well, this is great. I mean, could we now just make one single thread for every single element in our array? So now all elements at once, just all increment by 1. Will this give us incredible speed up? Or would that be a bad idea to make like a ton of threads? What is the issue with creating just an ungodly amount of threads on any program? Yeah. Yeah, context switching, right. Could you elaborate more on, actually, yeah, could someone else elaborate more? What is context switching? Yeah.
So switching from one thread to another thread is not free because you have to move in, let's say, register files or the data you had from the previous thread before it switched.
Exactly, right. So the operating system needs to keep track of all of the data that's associated with the thread. And all of the data, yeah, that means like registers, that means your stack, potentially means your heap. I guess actually heap allocated stuff should be global. So yeah, it'll be your stack variables and your register variables. And every time that you pull out some program out of a core, out of a physical like CPU core, that is an extremely expensive task. It could be like anywhere from like a kilobyte to maybe several megabytes that it needs to transfer data like into and out of a single core. And yeah, so this can be extremely expensive. And now if you are doing this like thousands of times per second for every single core, because now you have this program with thousands of threads that you need to try to make sure that every thread is like equally fed into your core. So every thread is, makes equal amount of progress, then that's just a lot of work for your operating system to handle. So for the most part, actually, being single-threaded is not a bad idea. It simplifies things, makes your operating system a little bit happier if you just have a single program. If you introduce all these threads, then it potentially slows down your computer a lot. Okay, cool. Wait, follow up? Yeah. Yeah. Mm-hmm. Sure. Yeah. So if you're building mission-critical software, like the brakes in a car, or maybe in like a rocket ship, or maybe something in a defense company. Sure, you really want to make sure that that software works no matter what. And basically one of the main theses that I talk about in the past 2 lectures, is that multi-threading is just really difficult. So in keeping everything single-threaded, it could potentially be a good idea from a security standpoint, and just making sure that everything works. But that's not always possible, because maybe you're Green Hills, and maybe the rocket that your customer is sending up into space wants to run a bunch of different programs on it. Maybe it wants to run something that senses the temperature of the atmosphere, and then another program that senses the fuel level and the fuel level, and then something else that monitors the speed. And so it's running all these like independent programs. Then the operating system needs to be able to handle that. And it's an extremely challenging task. And that's why Green Hills is one of the very few companies that actually makes mission-critical operating systems. Most of the time, if a software like crashes on your computer, you're like, oh, like that sucks. Like I'll just like restart it. If that were to happen, and a missile, it could mean a much more catastrophic impact, of course. Question? Oh, great question. Do you need more than one core to do multi-threading? Okay. Do we have any thoughts from the audience? Do we need more than one core to do multi-threading? In the back, Either one of you. You do not. Okay. Why not? Right, exactly. So if you have a single core, that just means that every thread will just need to we'll need to context switch in and out of that one single core. So like most computers in our lives have been a single core. It's only in the past 25 years or so that we have had multi-core machines. And before then, what you would do is, you would just spend a little bit of time running each program, and you'd run a program for maybe a couple milliseconds, and you'd swap to another program, run that for a couple milliseconds, and swap around, and you just keep trading them in and out. Sure, follow up?
So with context switching, is each thread runs simultaneously, or taking turns switching off?
Right, so in a single core machine, a multi-threaded application would not have anything run in parallel. A multi-threaded application can only have things run in parallel if you have multiple cores on your machine, if you have enough cores to run more than one thread of a multi-threaded application. Yeah.
I guess in that case, if it's not running in parallel, then what's the benefit?
Sure. So a big benefit of multi-threading that I have not talked about is security. Because imagine that you are writing an operating system, and now you want every application, like every user application that someone has downloaded off the internet or something potentially sketchy, vulnerable, you want that to be running on an entirely different thread that has entirely different memory rules and things. And so at your operating system level, it's very important to have everything running as a different thread. When you move up the stack and you're just writing a user program, then I guess I forget your exact question, but you do not need to use threads, I guess, on as you move up the stack. But it's crucial for operating systems. In fact, anytime anyone writes an operating system, it's half the code, I feel is all managing threads. The other half is drivers. Question. Sure. So that is a huge research area. The idea of like side channel attacks and yeah, trying to sniff out what is happening on other cores or sniff out what's happening on other threads. That is a huge bit of research. That's a $1 billion industry right there that I do not know too much about, and I can't really talk on it. But yeah, it is totally a potential security. There are security vulnerabilities that people could exploit. Yeah, one big thing is like related to caching, because you want each thread to run fast. But if a thread runs fast, then that means that it has stuff in the cache, and if it has things in the cache, then there's a chance that you might be able to extract some things from the cache. So things get a little hairy. All outside the scope of this class. Yeah, no, good question. Sure, okay. Cool. Any thoughts? Yeah? Sure, right, yeah. Most of the computer research world has been single-threaded. So yeah, it's only recently that computers have become dual-core more. But also, like my family computer growing up was a single-core machine until, I don't know, 2013. That was like when we got our first like dual core in the house. So, or actually, I think maybe it was a quad core, but yeah. Yeah, sure. Versus like this one now has 22 cores, which is like, it's like spicy. It's good. Yeah. Cool. Okay. Good. Cool. I want to talk about locks now, though. So the idea with locks. Can anyone describe a case in which, what's a good question I can ask? Okay, no, this is good. So, yeah, okay. Hopefully we remember this example from the lecture. So the idea with this is maybe we have Ethan's bank account balance, and let's, fictitious, let's imagine that I have $1,000. Like, I don't know where I got $1,000, but let's imagine that I have $1,000. And then now let's imagine that my friend Rob and we were on the phone with each other, and maybe at the exact same time, we both tried to withdraw $100 from this account. I'm like, okay, Rob, okay, ready? And 3, 2, 1, go. And we both click at the same time. And now these threads, maybe it's on this. It's not on a single core machine. Instead, maybe it is on a 128 core machine running somewhere. At the same time, these two cores, one of them is Rob's thread, one of them is running Ethan's thread, and they both subtract 100 from Ethan's balance at the same time. And what you could potentially have is, since they run at the exact same time, you may have the case where Ethan's balance is decremented to 200, but then since they were both loaded as 1,000, then when Ethan goes and decrements as well, then it will stay at 100 or stay at 800, and then in total now. Oh, I guess I said the numbers wrong. Assuming that they both decrement, they pull out $200. Sorry. Okay. Let me rephrase this. Assume that I pull out $200, Rob pulls out $200. You should imagine that we should be left with $600. But we have this case here where, due to context switching, instead we are left with $800. So we have magically stolen $200 from the bank, and that is because we both tried to grab the data out at the exact same time. Okay, so does anyone remember the solution to this? How do we make it be where if someone tries to change a bit of data, someone else tries to change a bit of data at the exact same time, that the data is properly handled, and instead we don't have this situation where like Ethan first loads $1,000, and then Rob then loads $1,000, and then Ethan subtracts 200, then Rob subtracts 200, and then in total we have this corrupted value. So okay, turn to the person next to you, tell them how did we fix this problem in the lecture? Okay. How do we fix this? Okay. Oh, yeah, fix it. Yes. Say that one more time. Yeah, exactly. So we want to lock this resource. The resource would just be Ethan's balance. So in the program here, so I actually wrote this program out in C. The solution was right here. We have this withdraw function, and now we just add this lock right here. Okay. And I really like the idea of thinking about this as if it was a bathroom, that each of these threads, so imagine we have two withdraw threads happening at the exact same time, and they both are racing to the bathroom as quickly as they can. They get to the bathroom, and only one of them can go in, and they lock the door behind them. And the other person tries to go in and tries to lock the door behind them, but it's already in use. So now they have to stand outside the bathroom, and they have to wait until the bathroom door becomes unlocked. And while one thread is waiting for the other thread, that thread goes about its business and decrements balance by amount, and then goes in and leaves the bathroom and unlocks. Then after that, the operating system will recognize that one of the threads was waiting for this lock, but this lock has just been opened. So then it will schedule now the second thread, now schedule it back into the operating system where now it can call lock and enter the bathroom and lock the door behind it, go about its business, then go and unlock the door. So this is the solution. And notice that, we are able to perform the entire action, seemingly simple, but actually fairly complicated action of just decrementing a value by an amount. Because in order to decrement the value by the amount, remember in this assembly example, there were actually 3 separate instructions that needed to be run. There was load, there was add-I, and then there was store word back. So even though it's just one single line of code, we can still within this have an interleaving of instructions. And so we would need to add this lock around this. Okay, hopefully this is a good review from 130. Okay, any questions on this? Can make sense. Okay. Kind of funny question for you. What would happen now if I got rid of this line right here? What would happen? Okay, tell the person next to you. What would happen now to this code if I remove this line? All right, I'll go and run it. Hopefully you are all in agreement. Okay, so what this code is doing is you can see it's running these two withdraws. And, the first withdrawal, it looks like it probably happened successfully, but then it never... Well, maybe it crawled out the window or something. Maybe it didn't actually unlock the door when it exited. Maybe the door is now just staying locked even though the business is done. And withdraw now is going to lock indefinitely. Okay, and you can see, so I just ran it, but it's not doing anything. It's not making any progress. Okay, so therefore running unlock, very important. Okay, cool. So what this is called when it just stalls like this. Is anyone aware of the word, the textbook word for what this is? Yeah? This is a deadlock. Yeah, okay. I want to switch to my iPad where I want to talk about one of the most common explanations or common analogies and problems in multithreading involving deadlock called the dining philosopher's problem. Anyone heard of this? Okay, I won't spend too much time on it. This is great. Wow. I was expecting on covering this so much, but it seems like you're all experts. So we'll just have a conversation together about this. Yeah, it'll be great. Okay. Do you guys like the dining philosopher's problem? You're like, oh yeah, this is my favorite thing that I've learned ever. Okay, so dining philosophers. It's the idea that maybe you have 5 hungry philosophers sitting around a table, right? okay? And they spend all their time thinking and being philosophers that they actually don't have enough money to buy enough chopsticks for all of them. So they need to share chopsticks, so they only have 5 chopsticks. And the way that the philosopher's life works, it's a very complex life, but what they do is they sit at this table all day, they think. And occasionally, they do something else, they eat. And what they do is they will pick up a chopstick on one side, they'll pick up a chopstick on the other side, and then they'll eat for some amount of time. Then they will put down the chopstick on one side, put down the chopstick on the other side, and then go back to thinking. And each one of them is going to do this. Okay, so yeah, we'll have maybe this philosopher 0 right here, picks up one chopstick, picks up the other chopstick, and then we'll go and put them down. We might have the case where one philosopher picks up a chopstick, and then another one across the table picks up them. I mean, each philosopher we can think of as a different thread, right? We'll notice that when 2 philosophers like this are both holding both the chopsticks, well, now none of the other philosophers are allowed to eat. And this is probably fine, right? Most of the time they're going to be just thinking. But there could be a case where, well, one of the philosophers gets really hungry, and, well, they look to their left, they see a chopstick, so they go and grab it. Well, then they look to their right, and is there a chopstick on the right? No, okay. So therefore, they must wait for what? You can just shout it out. What must this philosopher wait for? Yeah, exactly. It must wait for the chopstick from the one above. So maybe now this philosopher will let go of its chopsticks because it just finished eating. Well, now this philosopher can start eating. Yeah. Okay. This is called lock and wait. So lock and wait is the idea that you are holding a lock while you wait for another lock. Okay. Also notice that things are mostly okay in this situation, right? All you need to do is just kind of wait for the philosopher to the next, like to the side of you. If they're currently eating but you're hungry, you just wait for them to finish. Not a big deal. Wait for them to finish, and then you can get the chopstick when they're done. Okay. The question, though, is there ever a chance for this to deadlock, where none of them can make any progress? Okay. Tell the person next to you, remind them from CSE130, be like, yes or no. Explain to them why this or cannot deadlock. Go and remind them. Okay. Can this deadlock? Okay. Maybe someone from like this side or in the back. Anyone? Is that all? Yeah? Oh, so, wait. Sorry, I did not pick on you. Wait, behind you? Yeah. You? Right here? Yeah. What was that? It can deadlock. Okay. How can it deadlock? What's the situation when they deadlock you? Okay, so every philosopher, they pick up the chopstick to the right at the exact same time. Okay, so let's quickly check. So if this one picks it up, okay. And then they reach to the other chopstick, they're like, oh no, does not exist. Therefore, it's going to wait. But I'm holding one chopstick, right? So it's like a stalemate. They're all waiting for the other philosophers to let go of the chopstick. This can absolutely happen. Yeah, and this is called deadlock. Also notice that there is something of a circular dependency here. So this is called a circular wait. So remember, we have a hold and wait problem where if you are holding a lock, you are waiting for another lock, but then also a circular dependency. And so these are 2 requirements to check for to see if you have a deadlock. So hold and wait. Okay, and then Okay, cool. Can anyone think of a, actually, well, I'll switch over to code really quick. Yeah. Great. Okay, so here I have the this dining philosopher problem kind of already implemented. So here we can see I have a philosopher thread, and all the philosopher thread does is it will think for 100 milliseconds, then it will try to eat. And notice, yeah, we have 5 philosophers here. And then the eat function right here, we can ignore this really quick. Okay. Oops. Okay. Good. So this is the eat function implemented. So here we pass in the ID, whether it's philosophers 0 through 4, and then we get the index of the left chopstick and the right chopstick. Then we go and we lock the left one first, then we lock the right one. Then we go and eat for 100 milliseconds. Then we unlock both chopsticks, same thing as like putting them down. Okay, so now your goal would be, really quick, let me go and run this just so you can see that it does deadlock. So if I go and run this, so I'll cd into philosophers, G++, /main, and, main, okay, eat.cpp. Okay, fantastic. So now it's running. And we could wait for a while. And in fact, this should deadlock from what I've showed you, but the chance that they all context switch in the perfect way where they all pick up the chopstick is fairly rare and maybe only happen once every year or something. And if this is a mission critical bit of code, like someone's breaks or something, then that is a really bad time scale. Instead, a better time scale would be deadlocks once every heat death of the universe or something. So in this case, it's not worth it. So let's increase the probability a little bit and just add another sleep function right here, just so that maybe they're a little bit slower at picking up their chopsticks. So I'll make them wait for 1 millisecond, and we should see that it should just deadlock right away. So yeah, immediately. So you can see that philosophers are thinking, then they go and they pick up their chopsticks, and then immediately they stop working. Okay, so the question to you now is how could you instead implement this eat function to where now we can lock both of our chopsticks, and we still have this kind of this array of forks here. Think how can we implement this to where now we avoid a deadlock? To where even if they pick up the chopsticks really slowly, that we're never going to have a deadlock. Okay, you can think back to CSE111 if you guys talked about this. Okay. Okay, I want you to really chat with the person next to you. I'll give you 2 minutes to devise a plan, okay, and then we'll chat about it together. I'll give you 2 solid minutes to chat. Can you think of a solution that avoids deadlock that still allows you to pick up 2 locks? Okay, think on this. Oh, and also assume that the chopsticks, you can only grab the chopsticks to the left and right of you. You can't grab a chopstick across the table or something. Okay, think about this for a couple minutes. Okay. Cool. So, any solutions? And by the way, this would have been a totally reasonable PhD project 30 years ago. It's come up with a novel solution to the dining philosopher's problem. Or imagine this, PhD dissertation, novel solution to the dining philosopher's problem. This is totally reasonable. Okay, comment. Oh, I actually really like that idea. Yeah. So maybe what happens is you pick up a chopstick and you look to the other side and you're like, oh, that chopstick to the side of me is taken. So you know what? I'll release this chopstick for a little bit, maybe until this chopstick on the other side of me releases. Yeah, totally reasonable. And that is called preemption, or the idea of dropping a lock after you've taken it, even if you not necessarily have actually achieved the outcome of that operation. For example, if you remember from the lecture that I just posted, the idea of a queue, if you want to check, first you want to lock the queue to check if the queue is empty, and then if the queue is empty, then what you do is you context switch away and wait until the queue eventually has something in it. Then you take the lock back again, and then you perform whatever operation you wanted. Yeah, so preemption, absolutely. And this is something else that is required for a deadlock. In fact, it would be no preemption. So no preemption is the idea that you do not release a lock even if someone else is using it, okay? Or even if someone else is using the other lock that you need, in a hold and wait condition. Okay, cool. This can absolutely solve it. Okay, another possible solution to this operation. Yeah? Oh, okay, I really like that. Yeah, so maybe you have one of the philosophers actually grab the other side. And what will that do? So which one of these is that going to destroy? Yeah, the circular dependency. Now, instead of having this circular dependency where this philosopher is waiting on this one's waiting on this one, this one's waiting on this one, this one's waiting on this one, this one's waiting on this one. Instead, if you just have one of the philosophers forced to grab the other one first, well then now, we break this chain, and instead, now this one would rely on both sides first. Sure, absolutely a solution, yeah. Okay, anyone think of another solution? So there are several, but those are kind of the biggest ones. Another possible solution is, maybe what you do first is you check are both chopsticks currently in use? And if they are in use, then, if either one is in use, then I'm going to wait for a little bit. And then the next time that I want, then I can go and try to grab both of them if both of them are available. And in that case, it waits for both chopsticks to become available before it will actually go and grab them. Oh, yeah, question? Right. So you would still need to have some sort of preemption where after you've tried to lock both of those, it adds a little bit more security. Maybe it gets your p-value a little bit lower, the chance of deadlocking. Right. So you still have a potential issue, but so you just need to make sure that you eliminate fully at least one of these. Yeah. Okay, cool. And then I guess a final kind of requirement of this is that you also need to have some sort of mutual exclusion. Or in other words, a mutex, mutual exclusion. So mutex. Okay, so these are the 4 requirements for a deadlock to happen. talk about the questions really quick. There was a question about what mutual exclusion is. There's a different word that I've been using instead for this. It's like an abbreviation of mutual exclusion. What is that word? Yeah, mutex. Yeah. Okay. So mutual exclusion, is the idea that only one thing, one thread, can operate on one resource at a time. Yeah, mutual exclusion. Also called, like, I don't know, atomic variables or something. Okay, cool. So which of the following statements about threads and CPU cores are true? So a core is a physical part of the CPU that runs threads. I think so, yeah. The number of cores in a system limits how many threads can exist. Yeah, because we can have a single core running as many threads as we want, right? Okay. If there are more threads than cores, the operating system has to switch between them to run them all. Yeah, cool. Okay, that's the whole point of the operating system, basically. It's just context switching between all of the different user programs. Okay. Question 3, which of the following statements about multithreading and performance are true? So switching between threads takes time and has a small cost. Yeah, okay. What is the word that I kept describing, like what this is? This is context switching, okay? More threads always makes a program run faster. Yeah, and not really, okay. Sure. Too many threads can slow things down because of too much switching. Yeah, actually, yeah, okay. Even if a program has only one thread, the operating system still switches between it and other programs. Yeah, this is still true. Yeah, you could have a mouse driver that is running in parallel with a GUI application that is running in parallel with, I don't know, some virus that you have on your computer or something. It could all be running in parallel. Yeah, okay. Which of the following statements about how threads run are true? Okay, the operating system decides which threads run at any time. Yes, okay. The operating system makes sure each thread finishes before switching to another thread. Yeah, no, okay. When will the operating system switch to another thread? Yeah, it's up to the implementation details of the operating system. From our perspective, it could happen at any time because we want to write code that could work on any operating system. So from our perspective, it shouldn't matter. Okay. A program with multiple threads will always run them in the same order. Okay. Yeah, not necessarily. You could have the operating system choose to run everything like backwards for some reason. Okay. The order in which threads finish is not predictable. Yeah, yes, okay. This is kind of a bummer of a question, actually, I guess. It was just like the operating system controls everything. Okay, this question. Which of the following statements about locks are true? If a thread tries to use a locked resource, it must wait until it is unlocked. Okay. Locks help protect shared data so multiple threads don't change it at the same time. Okay. After a thread unlocks a resource, that lock is freed from memory, never to be used again. Yeah. I would say no, right? Because the whole point of a lock is that it can be used by like any thread. Any thread can lock it, unlock it at any given time. Okay. Okay. Which of the following are required for a deadlock? Select all that apply. Okay. Is hold and wait required for a deadlock? It is. Okay. Is it possible to have a deadlock if you do not have hold and wait? Is it possible to have a deadlock if you do not have hold and wait? It is not possible. Right. What about circular wait? The idea that two threads are like circularly depending on one another. Yeah, this is required. Okay. Okay, no preemption. Is this, it's kind of a weird double negative, but will adding preemption disable deadlocks? Yeah. There we go. Hope that was clear. Okay. Mutual exclusion, also known as mutex. Yeah. Is this required for a deadlock? Yeah, this is pretty obvious. Yeah, you can't have a deadlock if there's no lock. Okay. Do you need a multi-core machine? Yeah, this could happen on a single core machine. Okay. Any final questions on this? Okay, yeah, question. No preemption is something that will potentially cause a deadlock. Yeah. Okay. I want to actually mention one more really quick thing. There's a really good question. So feel free to put in the last quick little answers into the quiz. I wanted to, just mention one more possible solution to the dining philosopher's problem that could fix things. So another very common solution, and probably the most common solution that I've actually seen, is let's keep our voices down, just last 2 minutes of class. So the most common solution I've seen is actually to have kind of like a queue of which threads are currently active, and then also which locks each thread will need in order to proceed. And so what you have, you have this queue. And maybe you have philosopher like 0 at the top, then 1, then 2, then 3. And maybe philosopher 0 comes off the queue and then grabs both of its chopsticks. And then number 1 will come off the queue, and then we'll see like, oh, okay, I cannot grab this chopstick, so I'm going to wait, and now this queue is going to stall. And this kind of stinks, right? Because now only one single thread is working at a time. But what this means, and honestly, this is kind of rare. You generally don't have blocking after just like the first single element. But what this now means is that you are checking like in a queue. It's like what threads are able to be run. And let's say instead maybe it was reordered like this. Then we could pull off element number 2, and now element number 2 could start working in parallel. And so if you have maybe like 20 threads all working at the same time, then now you can have this queue, and it will pretty much guarantee that it will guarantee that there's no deadlock, but it will also pretty much guarantee that every thread will be given approximately the same amount of time in total to eat. So now every thread, like there's no one thread that will like starve. That's another concept, is starvation. So this is a very common solution where you have a queue that keeps track of each thread and then what locks it requires. Okay, any final questions on this? Yeah. You check if the locks are available before popping something off of the queue. Yeah, thank you. Okay, any other final thoughts? Say that again? Exactly. The queue is based off of the locks available. Yeah. Okay, cool. I think that is a good place to leave off. I will see you all on Wednesday. We're going to talk about exceptions and maybe some other things. Okay, look forward to it.